Hi everyone, this is the first video on limits for Math 1451 at Texas Tech University, which is Calculus 1. So in this video, we're going to be talking about what is a limit, when can we find it, and when can't we find it. So given a function, a limit tells us what we expect the function to do, even if that's not necessarily what the function does. So we're going to be looking at this graph that we have here, and we're going to specifically be looking at the x value 0. So when x equals 0, we can kind of trace along the graph, and I'm just going to trace the graph maybe a little bit thicker than it currently is. So as we move along the graph, well, at 0, we see we have an open dot, and then we can continue on the other side of it. So because of that open dot, we say that the function is undefined. So this is something that you should be familiar with from your high school math courses. Let me write that a little bit better. This is undefined. At x equals 0, because we have that open circle in the graph. So the graph's undefined at that point. However, whenever we trace that graph, we skipped over a certain point. So when we were tracing that graph, we skipped over the y value of 2, right? This is aligning right at that y value of 2. And that's what we would expect the function to be at whenever we were tracing along and got to that open circle, because we have an open circle at 0, 2. So we expect the function to be at 2. And we're going to call that the limit. So we're going to say that the limit as x goes to 0, and so that's what's given to us here as x goes to 0. And this arrow is representing that we're tracing the graph, right? So we're moving closer to 0, and we would expect the function to be at 2. And we say that the function has a limit value of 2 at x equals 0. So the function is undefined at this point because we have that open circle. But if we look at the larger picture of the graph and look at what is happening around that point, we say, well, we just have an open circle at 0, 2. But so the graph would be at 2 if everything went according to plan and we didn't have this open circle. So in this case, our function value is undefined and our limit value was 2. So you may ask, well, does the function value ever match the limit value? And the answer is sometimes, but not always, right? So if this graph just had a filled in circle here, then yes, our limit value and our function value would be 2. And so if we have cases where our graph is not continuous, so if there's a break in the graph in this way, then the limit value and the function value are likely to be different. So whenever we're evaluating limits, our first strategy is going to see if the function is defined at that value. And if it's undefined, we're going to try something else. However, I may caution you, just because the function's defined at that point doesn't mean the limit value is the same as the function value. So for example, in the graph up here, if instead of that point being filled in at 2, if that point was filled in here at 1, well, the function value would not be undefined, it would be 1, but the limit value would still be 2, because that's what's happening around the point at 0. So looking at the limit value is essentially zooming out, looking at the rest of the function and seeing what would happen based on what's happening around that point. And so once we say, okay, well, if my limit value is my function value, that may happen, it may not happen. Well, if it's not the case, then we have to try other ways to evaluate the limit, but that will also not always be successful. So for some graphs, this tracing of what the graph should be doesn't give one conclusive answer. And so we're going to look at the 3 scenarios in which this may occur. So the first one is different left and right behavior. So again, if we are going to trace this graph, this first graph from the left, going closer to 0, well, we should be at the point -1. And if we're tracing what happens after 0, well, that graph is a straight horizontal line at 1. So what's happening here is, so from the left, we expect -1. right? Whenever we trace from the left, we're at a horizontal line at y equals -1. But from the right, we are going to expect +1 because we have that horizontal line at +1. And so this is what's happening when we have different left and right behavior. So this essentially can be seen by a jump in the graph. So at the left of 0, we're at this horizontal line, and then we're going to jump up and something different happens on the other side of 0. So this is going to tell us that the limit as x goes to 0 of f of x, using that same notation as before, this does not exist, because what the graph should be, well, on the left, it should be a -1, and on the right, it should be a +1. So there's no good reason that one or the other should be the limit value. So we're going to say that this does not exist, and most instructors will abbreviate this D and E. This limit does not exist, because we have this kind of jump and quick change in the graph. So the next thing is when a graph oscillates. So if we're going to trace this graph here, what's happening is that we are kind of jumping back and forth between 1 and -1 from the right, and then from the left, and then from the right, we're also doing the same thing where we're jumping back and forth between 1 and -1 very, very quickly. You can see the graph gets kind of messy there in the middle. And so this is called oscillating behavior. So what this is that the function is going to bounce back and forth between -1 and +1, right, as we're getting closer to 0. And so we're going to say that same thing here, that the limit as x goes to 0 of f of x does not exist, because it's going to bounce back and forth. So just like case 1, well, it's going to flip back and forth between 1 and -1, and there's no good reason to pick one or the other for the limit value, so we're just going to say it does not exist. And finally, we're going to look at unbounded behavior. So we can see we have a value of pi, and this value here is going to be at pi/2. So some of you may remember from your previous math courses that we have these dotted lines that are going to represent asymptotes. So if we do the same thing and we trace this graph as we go closer to pi/2, well, that graph doesn't stop. It keeps on going. So if you remember about asymptotes, that our functions get really, really close to those values, but don't ever actually touch them. So if we're never actually going to touch that value pi/2, that just means that this line is just going to go up and up and up to infinity. So the function increases without bound, and that's why we call this unbounded, right? So if we can never touch that value of our asymptote line, then we just are forced to keep going up, because we can't go any more to the right to cross that asymptote. And so the way we write this is that the limit as x goes to pi/2 of this function, again, does not exist. So these are 3 different cases in which the limit doesn't exist. So we can have different things happening when we go from the left and the right. We can have different things happening from a single direction if we oscillate back and forth between values. Or lastly, we could have this function never really approach any finite value, and then it's going to be an unbounded. So these are cases in which tracing the graph isn't going to tell us anything. However, you may see, okay, well, all of this has to do with tracing the graph, but tracing the graph isn't always a realistic option if we don't know how to draw the graph we're given. So we're going to switch now to look at some methods of evaluating limits that don't rely on us looking at the behavior on the graph. So your instructor may call these analytic methods, and they're just going to use the equation of the function that we're given. So first, we should try and see if the function value exists, and see if that limit value is going to match the function value. So if no function value exists or we get an indeterminate, we have 4 options. So option 1 is going to simplify the function by factoring. Option 2 is going to be rationalizing the function. So remember that rationalizing has to do with multiplying the function by something typically involving a square root on the top and the bottom, the same thing. The third option is going to be using special trig limits. So if you haven't gotten here in your course yet, that's fine. They should be coming. And these are just going to be limits for us to memorize. So if our function involves a sign, we can try and rewrite it to involve a fraction that has sine of x over x. And if our function involves a cosine, then we can try to rewrite our expression to have a 1 minus cosine x over x. So these are 2 special trig limits. Again, just for you to memorize. Your instructor may not have gotten here whenever you're watching this video, or they may not have talked about this second one, 1 minus cosine, because it comes from sine x over x. And the fourth method is going to be to use L'Hopital's rule. So if you've never heard this phrase in your life, don't panic, because this has to be covered later in the semester. So L'Hopital's rule is going to rely on derivatives, so we have to learn it after we get there. So this one is going to be later. So this one tends to be a favored method because it's a little bit simpler. It relies less on algebra, and therefore we can make less algebra errors with this method. But we're not going to cover it in this video because we need to know how to do derivatives first. So this is kind of an overview on limits. But like I said, these 4 strategies are going to be for cases when drawing the graph isn't realistic and we're just going to need to use the function to figure out what our limit value should be. So we're going to come back in our next video and work the examples. So that's all for this video. We hope this helps, and good luck.